Welcome to Math 31, Introduction to Calculus. We are in our last lesson looking at the derivatives of logarithmic and exponential functions. And today we're looking at a strategy called logarithmic differentiation. And we looked at this actually, an example of this, in our previous lesson. So let me jump back to that lesson and where we used it. And here it is back in question 11. Where we were asked to find the derivative of 2 to the exponent x. And this is before we had a rule to do it. So what we did was suggested here in the brackets to take the natural logarithm of both sides and then use implicit differentiation. That's logarithmic differentiation. So our first step was to take the natural logarithm of both sides. And then that enabled us to use the law of logarithms to take this exponent of x that we had here and multiply it to this logarithm so that we're multiplying these two exponents. With the x out of the exponent, then we were able to take the derivative of both sides with respect to x. And this is where implicit differentiation came into it. We had a 1 over y times dy dx. And we're going to see that that happens every single time we use logarithmic differentiation. From here, we just isolated the dy dx, and that's what we got up there. And then here we wrote our final answer. So let's go back to the lesson and use this process on a few fairly complex functions. Now for this one, you'll want to be conservative with the space that you have. So try to write small. I think I didn't leave enough space in the notes, but here we go. Step 1 is take the natural logarithm of both sides. So I have the logarithm of the left side, ln y, and the natural logarithm of that entire rational something or other on the right-hand side. Doing this will show us the power of logarithms to take complex expressions and simplify them, because we have those 3 laws of logarithms. Let's say if I have the logarithm of a product, that means I can separate them into 2 logarithms and add them together. Or if I have a logarithm of a quotient, I can separate them into subtraction of logarithms. So what that does is it allows me to take this right-hand function and separate it into all these different logarithms. So in the numerator, I had sine x times cos x times tan cubed x. That multiplication of powers turns into this addition of their exponents. And then dividing by the square root of x, that division turned into subtracting the exponent. This lets us separate all those little pieces in that complex function on the right side so that we can do derivatives on each part separately. Now let's take this one step further before we actually take the derivative of both sides. And in this step, what we're doing is here, since I have a tan cubed x, that exponent of 3 I'm able to bring down in front of my tan or my logarithm function. And this exponent of a half that was with the x, I can bring that down in front of this function as well. Now we can take the derivative of both sides. There's a lot to do, but it's in smaller pieces now. So when I take the derivative of the left-hand side, derivative of ln y is 1 over y times dy dx, as we saw in question number 11 from our previous lesson. Here, the derivative of the natural logarithm of sine x, derivative of the natural logarithm is 1 over its argument, so the 1 over the sine x, that inside function is unchanged, times the derivative of sine x, which is cos x. Similarly, derivative of ln cos x will be 1 over cos x times derivative of cos x. 3 times the derivative of ln tan x will be 3 over tan x times the derivative of tan x. And then 1/2 times the derivative of ln x is 1 over 2x. Well, this is fairly long and complex. I'm just going to collect some terms together here. So the cos x over sine x, the negative sine x over cos x, and the secant squared x times 3 all over the tangent x. So all of those I simplified, and then this y that was in the denominator on the left, I'm going to multiply to that entire function on the right. Because again, my goal was to find what is dy dx. What is the derivative of y with respect to x? Well, we have one more step to go. Just like we did in question number 11, when I multiplied the y to the right-hand side, I didn't want to leave it as y because my original function was y as a function of x. So I replaced the y with the x squared. So now in this question, I want to do something similar, where I want to replace this y with what y is equal to from my original equation. And there you have the final answer. And we don't bother simplifying. We just wanted to find a derivative, we take it to here, and then we run away. But what it's done is it's let us take the derivative of this really complex function without using multiple product rules and chain rules and quotient rules altogether. We could have done it a different way, but this made it so we could break it down into smaller steps. That's what logarithmic differentiation does for us. But it also does something else, as in question number 2 here, we have a base that's a function of x, and we have an exponent that's a function of x. Well, the base as a function of x, we would think that we would use the power rule. But where we have an exponent that's a function of x, we would think that we would use the exponential derivatives. But this is a mixture, so neither of those will work. The only way we have to take this derivative is logarithmic differentiation. So again, we begin by taking the natural logarithm of both sides. Once we've taken the natural logarithm of both sides, we will use the law of logarithms to simplify that expression that we have. And in this case, we'll take that exponent of ln x and multiply it down in front of the natural log of the x squared plus 3. Now we're ready to take the derivative of both sides. We still have a product rule on the right because we have these two natural logarithm functions where the first one is just natural logarithm of x, and the second one is the natural logarithm of x squared plus 3. So back to my messy handwriting. Derivative of the left, again, 1 over y dy dx. On the right-hand side, I have the first function, ln x unchanged, times the derivative of the second function, which is 1 over x squared plus 3 times the derivative of x squared plus 3, which is 2x. So I didn't have that written in here. And then I have my second function times the derivative of the first. Then finishing off the question, there are a few things that happened. First of all, this y that was in the denominator got multiplied up to the right, and right away I replaced it with what y was equal to in our original equation. So here we knew that y was equal to x squared plus 3 all to the exponent x. Next, I just simplified this expression and the next and kept them inside brackets, and that's where we stop. So we don't do any further simplification. If we wanted to find a slope, then we just plug in values for x and we'd evaluate from here. Let's look at another example. Well, maybe not. Check your understanding. Pause the video at this point, try this question, and then restart once you have finished this question. We start by taking the natural logarithm of both sides. Next, we use the law of logarithms to separate this complex expression into a sum and difference of logarithms. And then we can use that third law of logarithms that lets us take exponents inside the logarithm and write them as multiplication in front of the logarithm. And at this point, we are ready to take the derivative of both sides. Having taken the derivative, we can simplify the right-hand side a little bit, and we can multiply the y value over to the right-hand side. And that finishes the question. We have a couple more check your understanding questions. Why don't you work through those and then restart the video after you've finished question number 4, and then on the next page there's question number 5, and that's the end. So pause the video at this point and try those next two check your understanding questions. So here you see the first few steps in the process where the logarithm has been taken of both sides and the exponent of 1/3 has been brought down, and then the logarithm is separated into addition and subtraction. And notice that 1/3 needs to be multiplied to each of those separate logarithms on the right-hand side. So here I've shown that 1/3 being distributed to each of those logarithms. And now we're ready to take a derivative using implicit differentiation. And notice here when we take the derivative of the cosine, we get a negative sign. So this addition turned into a subtraction because this sine of x is a negative, being the derivative of the cosine of x. Then we'll multiply the y over to the right-hand side and we're done. On to the last question. And you'll notice that I combined a couple steps together here, taking the logarithm of both sides and then at the same time bringing that exponent of sine x in front of that natural logarithm. And then I still have a natural logarithm of x inside the logarithm that I just took of the right-hand side. From here, we need a product rule to take the derivative. So we have the first function, sine x, times the derivative of the second function. And when we do the derivative of the second function, we do 1 over the ln x, so that's the inside function unchanged, times the derivative of natural logarithm of x, which is 1 over x. And then plus the second function, the ln x, times the derivative of sine x. And we're ready to multiply the y over. And that will finish our question. There we go. We have finished the derivatives portion of this course.